sunk costs. And so that's where we're going to get into now in module 3. How are we really going to compare costs adequately across options? And how are we going to make sure that those costs are supported in the future? So really getting into sustainability first, right? Remembering that solar water pumping, and this is the first point to make to any user community, it isn't free. The sun's free, and this is a motto here across Latin America. Water is free. Feel free to go to the well, feel free to go to the river and gather it. What isn't free is the service. So this is a way to sort of get around the idea of users complaining that, oh, water is a human right, we shouldn't have to pay for it. True enough. You're not paying for the water, you're paying for the service to keep that water flowing at high quality. So for solar water pumping, we've gone a long way to really get over just the consideration of initial costs, right? Advocates of solar water pumping have done an excellent job of this, of really showing that it does pay for itself over time. But unfortunately, it's still very common to find systems that don't consider midterm costs, right? Capital maintenance expenses in their operation and maintenance plans, right? Very much so for community-based management, which is Green Empowerment's sort of greatest area of expertise. But even in community management plus systems or small utility systems, it's still common to find areas where there isn't a management plan that really takes into account these CapManX, right? We're only paying for regular maintenance expenses, and when there's one of these larger one-off costs, we're stuck scrambling to find how to pay for it. How do we pay for long-term capital expenses, right? How are we going to pay for replacement of sources, for replacement of pipelines? Over time is a question for the future, and an important one, but one that's much more global, right? Even in highly industrialized countries, most small water systems aren't capable of meeting those capital expenses with their own incomes. They're looking for grants, they're looking for government support elsewhere. So we don't want to necessarily recommend pushing those costs onto users, but CapManX really does need to be part of our considerations from the first moment that we're considering system design, right? So what is the community's ability to pay? And what is the community's ability to save? These are both critical, and in many cases, ability to save may actually be more complicated for solar water pumping, right? One of the advantages, although it's counterintuitive, of an AC grid system or of a genset system is that if you don't pay your fuel costs, you don't have water. And so that is a very strong motivation for communities to be up to date with their payments for water use, right? We've seen this example with some partners in Peru where communities have access to the AC grid. That access is relatively frequent. And these partners have proposed solar water pumping because electricity is quite costly in the area. That is a disadvantage, but we've seen that it's also a strong sort of motivating factor for communities to be up to date with their payments for water consumption. And a central worry in installing solar water pumping systems is you won't see those expenses happening. You'll still have significant CapManX, right? You'll need to replace your pump every 5 to 7 years. You'll need to replace your pump controller, but you won't have that sort of monthly or daily consideration of paying for energy. And so making sure that we have a bulletproof savings system that is really going to allow us to build those resources up so that they're on hand when a new pump needs to be purchased and the community or the maintenance system as it may be, whether it's a small utility, whether it's a private enterprise, has that resource on hand to replace the equipment when it burns out, can be a real concern with solar water pumping. So how do we consider adequate payment, right? One of the things we've really pushed for and we've seen be very efficient in even very small community water systems, we're talking systems with 30 access points, very small service populations, are water meters. Technician here installing one in a flood-prone area. But having water meters and really controlling consumption can be critical. And it's something that we've seen small communities willing to buy into, right? That there may be some initial resistance, but really working with the community from day one, right? From the pre-system design phase about needing to control water consumption is key, and something that we've seen water meters be something that communities can certainly manage, and something that can very much help to control the costs of operating our system. So as we consider these aspects of sustainability, what are the total costs we really want to meet? And here we want to look at life cycle cost analysis, right? We want to get over that analysis of just initial cost, just our initial capital expense. And we really want to consider what are our long-term costs for operating a system, analyzing in all cases the costs over the duration of the most durable system component. So when we looked at comparing things against solar, we're going to look at the most durable component of the solar system, which are the panels themselves. So we're going to be looking at 20, 25-year lifespans. And for our own use, and of course, something we'll be sharing with all participants in the course as you're interested in it, is a quick little Excel tool for comparing life cycle costs. So getting the accurate numbers to make decisions about whether solar is the right choice versus, for example, grid extension, versus, for example, continuing to use gensets, we want to get accurate numbers. So a couple of notes on this tool before we dive in. It makes no calculations beyond the cost of the system. It registers your assumptions, it registers the inputs, but it's unable to tell you, of course, whether those inputs are accurate or not. It just does the calculations. This is an early draft, right? We would really appreciate feedback from you all on what would be useful to see, what parts of this tool may not be working well, and really try to make something that's as useful in the field as is possible. This tool does offer the option to include a discount rate or inflation, right? Whether or not that's an appropriate tool for community-based management systems is an open question, right? Since we don't have initial capital going in, since we have costs that may not vary equally over the future, but we do offer the option to include that as we use the tool. And as I mentioned, it assumes that our solar panels are the most durable component and thus calculates the rest of our costs over the lifespan of those solar panels. So we're going to get into that tool here for a second. And of course, as we have questions on the tool, please feel free to interrupt, feel free to put things in the chat, and we'll make sure that we're explaining them accurately. So jump into the Excel here. Are you all seeing the Excel?
Yeah, maybe make it a bit bigger.
Sure thing.
Maybe close the recovery box.
We'll view that ever so slightly larger. Great. So, dock this to the top. Basically, in this sheet, the water that's required, right? Any required input is going to be in this light green, and anything that the sheet calculates automatically for you is going to be in these dark green boxes, right? So we'll need to go through. This sheet offers you the option to compare up to 3 different pumping options: pumping with the AC grid, pumping with a genset, diesel in general, or pumping with a PV system. And as we put in our unit costs, it will calculate our yearly expense for operating and display our comparative costs right here at the bottom. We hope that this is something useful as you actually do real world work. So leaving you a space here as well to put up the pump or the equipment data sheets so that you can use this as a reference tool, right? So this becomes a way to really record your assumptions for system design. So let's go through our example for Bianga again, right? As we recall, 50 cubic meters, 49.3, but we can call it 50 cubic meters of water a day. For our AC system, let's assume that we found a pump, Pedrolo, 2 horsepower pump, 220 volts, relatively affordable at $1,200. Please correct me, right, if this is not an accurate number for Uganda. And for all of these components, do wear out, we want to put in the component lifespan, right? How often is this Capman X going to recur over the life of our system? We've got recommendations here in the field. We've seen AC pumps last anywhere from 2 to 6 years here in Ecuador. In Peru, your experiences may vary. So really, we want you to follow your own experience as you use this tool and to sort of play around and see how small changes in component lifespan can really change the economics of the system. So assuming that we have a base cost, right, that regardless of how much energy you use in a month, you need to pay this fixed cost of $75. That we have an electricity cost in dollars or in local currency per kilowatt hour of 25 cents. And then what else is specific to our AC pumping system, right? Let's assume that we may need a larger bore conduction pipeline, right? What needs to be changed? What will wear out as we work? So let's assume we have a control panel for the pump, just soft start, a timer to control our pumping cycles, things like that. And then how long will those components last? So we are going to have them last 5 years. And now going back to what we mentioned in module 2, our reservoirs differ for pumping with AC or with the genset and what they would need to be for a solar system, right? With AC, with the genset, we assume that we can pump as needed, and thus we can keep our reservoirs significantly smaller, right? In this case, let's assume there's no water tower needed. We have a hill in Bihanga, and so we need a minimum of 15 cubic meters of storage when we're pumping at this flow rate. How did we get those 15 cubic meters? The calculation is there in that green empowerment spreadsheet that I alluded to earlier. And going to what our participant mentioned, right? How much does it cost to extend the grid to our pumping site, right? This is a one-time investment. This is not something that will wear out. Perhaps we do have transformers, something else that may have a limited time span, but we can include what wears out in a limited time span in this block and what's a permanent investment here. So let's assume it's $5,000 to extend the grid to our site. Let's continue to our diesel genset. All right. How large of a pump do we need? Right. Again, the system isn't going to automatically calculate this for you. You'll need an engineer that can tell you what size pump you'll need for your system. But let's assume we have a 3 kilowatt pump, assuming 65% efficiency, 0.4 liters of diesel per kilowatt hour delivered, right? We're going to automatically calculate our fuel consumption. We can get our pumping flow rate off our pump sheet, and thus we automatically calculate how many hours a day do we need to pump. So if we're pumping 2.3 liters per second, in 6 hours of pumping a day, we'll get those 50 cubic meters. We put in our fuel cost. We put in our average maintenance costs in dollars per year for our genset, assuming that we'll need to be maintaining it every couple of hundred hours, perhaps larger maintenance every few thousand hours of operation to keep our genset in perfect running condition. So a high quality genset here will last 35,000 hours under ideal conditions if we're really paying for that yearly maintenance. So you need to calculate by hand how many years of operations are we going to get out of a genset if we're running it 6 hours a day. In this case, let's say it's a 6-year genset, cost of the generator, again, correct me if I'm wrong here, $1,600 approximately for a 7 kilowatt genset, right? We don't want to use a rule of thumb. We can share the calculations for how we're making sure a 7 kilowatt genset is sufficient. But as you all know, in many cases, we're just eyeballing it as 2 to 3 times the size of the pump it's running. And in this case, using a 7 kilowatt genset for our 3 kilowatt pump. What does our 3 kilowatt pump cost? How long is it going to last? What other elements do we need for our genset specific system, right? Do we need a larger conduction pump line because we're moving more water? Do we need fuel storage? Do we need security for that fuel storage? What does that cost and how long is it going to last us for, right? Remembering that we always want to have the recurrence of these costs set up as accurately as is possible. Again, the cost of our reservoirs, including the tower if needed, same as it was for the AC system, 15 cubic meters. And now we get into photovoltaic, right? Here we have our breakdown, approximately remembering that we had a 8 kilowatt system. It was going to be costing between $24,000 and $32,000. Summing these, $35,000 minus the 96, right? We're right there at $26,000. So healthy within our range of $3 to $4 per watt of array. A solar pump going to last between 5 to 7 years in our experience. A lot of the literature will say slightly longer, 7 to 10. We would love to see that performance, but that has not been the reality we've observed in Latin America. So where that's possible, fantastic. We would prefer to be a little more conservative here to really make sure solar is the right choice. The panels and their support structure, of course, are our most durable item, so no lifespan for those. The cost of our reservoirs, and here we see the difference. Where we needed only 15 cubic meters of reservoir for the other systems, here we need the full day's worth of reservoir, 50 cubic meters. So a significantly higher initial cost than what it was for our genset, 3 times the cost, an extra $6,600. And then what's our balance of system, right? This is all of our wiring, this is lightning protection, this may be lighting for the pump house, and additionally things like security, things that may need to be replaced, right? Again, our lifespan, 15 to 20 years. And now our discount rate, right? The idea of a discount rate, 1 being the cost of capital, 2 being a way to judge for inflation. In some cases, we may want to set it to 0 if we really decide that we can't estimate accurately which direction component costs are going to go, which direction fuel costs are going to go, what our inflation is really going to be, and how that will affect system payments, as well as the cost of components. We can set it to 0%. Or we can also set it to higher discount rates if that's something that you feel comfortable using, or somewhere where you've seen adequate data at the country level to really estimate what your discount rate will be, right? A positive discount rate means that future costs are lower. A negative discount rate means that future costs are going to be higher. So for the moment, let's set it at 0. And in this situation, where we're using no water tower for Bianga, let's look at how our costs compare. For our AC system, our genset system, and our PV system, right? Our year 1 costs for PV are nearly 3 times what they would be for the other options. But we have no recurring costs until we need to replace our pump in year 5. Again, no recurring costs and pump controller replacement successively. For our genset, we're paying fuel every year, we're paying pump replacement every 3 years, and we're paying for maintenance. AC, we're really just paying electricity and pump replacement. So let's see how that maps out over time. As you can see, we've got our PV costs here, much higher in year 1, but quickly begins to equal out with the cost of our genset. In this case, AC is always going to be cheaper. If we do a grid that's close, it may be a reasonable choice. You know, right? It may not be reliable. It may not be close enough to extend. But in this case, after 6 years, our cost of installing the PV system is already, in some respects, paid for itself, right? The investment we've made in PV, assuming a brand new system, is equal to what we would have spent on the genset. If we want to assume a higher discount rate, these same data, let's assume that we have a very high discount rate, but one that I've seen used in the literature for sub-Saharan Africa. Our calculus changes a little bit. Now it doesn't pay for itself after 6 years. It's paying for itself where the costs are equivalent after 8 years. Now, let's see what this example would look like if indeed we needed to use water towers, right? So let's eliminate AC for the moment. Let's assume that we don't have AC available on site. We'll ignore these costs for the moment. Let's assume we needed a water tower for 15 cubic meters. We recently built one here in Ecuador that cost us about $8,000 just for the water tower construction, for 15 cubic meters. So let's add an extra $8,000 to that cost. And for our PV system, we don't need to elevate 15 cubic meters, we need to elevate 50 cubic meters. So let's assume that scales approximately, and rather than $8,000, we're going to be spending $24,000, 3 times the cost there to build a water tower sufficient for our solar system. Everything else holding the same with no discount rate. Solar is approximate equivalent here after 9 and really only starts to show an advantage after 11 years, right? So the payoff time for our solar system versus our genset, much larger. And if we have a discount rate, even more time, right? If we have a healthy discount rate, if in fact future prices are cheaper, you can see that over the life of the system, solar actually never is equivalent to the genset cost, right? So seeing how water towers and that initial expense on them really can be definitive in terms of determining what the most cost-effective solution is. And of course, these are calculations for brand new construction. You may already have a genset on site, you may have sunk costs there. And so figuring out what your current value of those sunk costs are, if you want to integrate that into this tool, what I would suggest is applying them as an additional cost to your other options, right? So let's assume that we have $5,000 in sunk costs. All right, let's take away those water towers and assume we have $5,000 in sunk costs already in a genset, right? We can just add that to solar, pretend that's an additional expense in our solar system, and remove that from our genset system. And that way we can see what that extra sunk cost looks like in terms of our comparison. Solar will pay off a little later. So we hope this tool is useful to you as you compare costs for what system implementation looks like. Any questions on this we'll get to here, since we didn't have anything in the progress. I'd also like to hear a little more commentary from everyone else around these questions on economics. Solar water pumping systems, right? In many cases, we just sort of hear, solar is cheaper in the long run. There's no fuel costs, end of discussion. But in many cases, really, the economics are more complicated. For one, what we mentioned about how do we save for those recurring CapManX expenses? What local structures exist that can be secure savings institutions, right? Where can we slowly save up $5,000, $10,000 and know that it'll be available after 5 years? Or what local actors, utilities, local governments, can really ring fence resources to make sure that they're available when that CapManX is needed? Another, how can we include the not exactly economic considerations of benefits that solar water pumping offers, right? There are real greenhouse gas benefits and even more real health benefits when we don't have to have population living around a diesel genset running 12 or more hours a day. How can we factor those into our calculations? How can we try to put a value on those? How can we use those as a tiebreaker, perhaps, when we're considering other expenses? And how can we consider the costs of system downtime, right? A solar system really should be functioning without much ado during many years, right? We won't have to fight with a supply chain for fuel. We won't have to fight with regular blackouts with our grid system. So how can we add value in our calculations for those solar considerations? And finally, how can we think about whether our system will change in the future? Easy enough to add more hours of pumping if we have a genset. That's more difficult with the solar system. So thinking pragmatically, how likely are our communities or our sites to see large changes in the future in terms of their water consumption? So I'd love to hear feedback from the group on this, and of course, any questions around the tool or around how we can continue to do cost considerations when we really are looking at multiple pumping options.
Guys, if there are any questions, you can feel free to unmute at this point, or you can post them in the chat.
Appears we have something in the chat.
Yep.
Yes, Sam, I'm sorry, when you started presenting the slides, it shows the presenter slides.
Ah. Very good. Thank you. Excuse me. Fantastic.
Here you go, thanks.
Of course. So is that the comment in the chat, or do we have a question there?
It was just, Igor was just doing a comment, not a real question.
Okay.
Katya, you have a question, go ahead. You can open the mic and ask the question if you like, Katya.
Yeah, well, I just was texting about the genset emissions. I don't know, I'm not sure now if we have like previous information about it or general data and in other projects, or if like we can compare it with emissions from conventional systems.
Hello, can you hear me?
Yes.
Yes.
Yeah, actually, thank you, Katya, for that question, because it led me to question, is it, do you have any case studies or examples where somebody has used the emissions reductions obtained by virtue of a solar system to sell them as carbon offsets in the market and compensate for that, to dampen the time it takes to justify the investment?
I'm not aware of any cases where that's been used, but especially as solar begins to hit scale, packaging systems and selling that sort of unified greenhouse gas benefit may be quite interesting. So that's a topic to certainly look into a little more and see if it might be viable once you are ready to install many systems, right? A single system, as with so many other carbon credit programs, it may just not be worth the paperwork, right? The economic benefit that comes out is often small enough that you really need to package hundreds, if not thousands, of systems to have the process make sense. But there may be actors that are already doing that. It would be interesting to look and see if there were any local examples in the country where solar water pumping really has taken off.
Thanks, Igor. Yeah, so there's another question from Norbert in the chat regarding cost comparison. Have you simulated other methods such as internal rate of return, NPV? So that's the question from Norbert.
We have not designed a tool to simulate other cost comparisons, but if that's something that would be of interest to other participants, right, we're going to be sharing a post-course survey, and if that's something that really would be attractive to have as a tool, that's absolutely something we could do.
Okay.
Moses has his hand up. Moses, please go ahead.
Thank you so much for the presentation. I'm looking at the comparisons, and I've seen that it is good, but I'm looking at a situation whereby maybe it is a project, a donor project. The donor have brought in some money, and this money is to help the people, like where I work in Karamoja. The people cannot afford to do that maintenance costs, maybe by using a generator. And the only option which we would think of is using the PV solar system, whereby the cost, at least the people could be able to maintain. That is maybe the cost. Since the maintenance, the operation and maintenance costs are much lower, though we have seen that the total cost may be compared to the generator system will take much longer time to do. But if the donor, it is better to go even for the solar system, even if it would take much longer time to meet that cost, since the benefit will be for the community, rather than thinking of maybe just money to buy the generator. Because with the generators, you could see that in rural places, the cost of the spare parts and even the availability of the spare parts themselves are very rare. And two, also the diesel costs are very high in such places like northeastern Uganda, which is Q. And I would say PV solar system, as we are doing, than going for the generator system, since the operation and maintenance, as we've tried for some systems with generators, that the generators are left there without being operated. There are some systems which we did with the PV solar system being backed up by a generator, but you would find that after 1 year, the generator is completely damaged because they are not caring for it. Thank you.
And yes, certainly the cost comparison tool is a way to sort of support our arguments around what the best long-term option is, but B, and we'll get into this in just a moment a little more, around how we really need to be thinking about water tariffs or collecting funds from outside donors, local government, other potential resources to support ongoing operational costs, right? We really believe that communities should be capable of supporting those costs on their own, and that needs to look beyond just day-to-day O&M costs to really include the replacement of components as that activity comes up, right? The generator may be abandoned within a year, but it would be a shame to see the exact same thing happen to solar after 5 years, once the pump burns out, right? No component will live forever. And so really thinking about how we make these systems sustainable rather than just how we punt these issues a little further into the future by using a system with lower O&M costs. Do you have any other questions there in the chat? I apologize, it's not opening for me without blocking the screen.
No questions yet, Sam.
Okay, fantastic. So it's a great introduction, Moses, to our last module, which is around how are we going to design for sustainability and how are we going to avoid sort of the most common modes of failure, right? How are we going